Hello, this is Hamid Tabianian from University of Padua. Before getting into the presentation, I would like to thank the organizer for giving me the opportunity to present my work at AQIS 2020. In this presentation, I will talk about the recent research on semi-device independent quantum random number generator based on energy bound. This work is done with Marco Avezzani, Professor Paolo Villoresi, and Professor Giuseppe Palotti. This presentation is divided into two parts. In the first part, I will talk about the semi-device independent quantum random number generator with E outcome. This is a theoretical work which we present a general framework of this semi-device independent protocol with unbounded outcome. In the second part of this talk, which is actually recorded in an alternative video file, I will explain experimentally implementing this semi-device independent quantum random number generator with exploiting heterodyne detection. Both work are now on arXiv, and you can find them with these two identifiers here. Here is the content of this talk. I start with introduction, then I'll move to quantum random number generator and different ways of generating quantum random numbers. Then I'll explain the general framework and secret estimation of this protocol. Later, I'll talk about two well-characterized continuous detection scheme, say homodynamic and heterodyne. And I finish the first part of this talk by considering many outcome approach. Later, in the second part, which is, as I said, in an alternative video file, I explain experimentally implementing this semi-device dependent quantum random number generator, and I'll show the experimental result. I will conclude both presentation in the conclusion. Okay, here is the definition of randomness. A string of numbers called random if it's uniformly distributed and unpredictable. Lack of any pattern or algorithm leads to predictability of this random sequence is very important. So a practical random number generator should be secure or unpredictable, high rate, easy to implement, and also affordable. But why random numbers are so important? Random numbers have many applications in science and technology. For instance, in simulation, gambling, and more importantly, in cryptography. Consider there are two parties on Earth who want to communicate through a public channel. Let's call them Alice and Bob. And the public channel can be a satellite. Alice wants to send a message which is wrong to Bob. So her messenger converts the message to a binary code, which is a mixture of 0 and 1s. If she sends it through this public channel, since it's a public channel, everybody has access to it. So a third party can intercept the message, reads it, and possibly change it. An easy solution to this problem is to combine the original message with a random key with the same length of the original message. In this way, as long as the random key is private, the communication is secure. Then Bob can have the original message by subtracting the random key from the received message. Distributing the random key between two parties is another topic which I'm not going to cover in this talk. With this example, I showed the importance of the random key secrecy or security of the random key. There are mainly two types of generators, classical and quantum. The first type, which is classical generators, the generation of random numbers is based on a deterministic phenomenon. No matter how complicated is this phenomenon, still it is deterministic, so it is predictable. Therefore, it is not secure. While in the other type, which is quantum random number generators, the generation of random numbers is based on intrinsic random behavior of quantum mechanics, which is truly unpredictable, therefore it is secure. Quantum random number generators are mainly classified into three categories: trusted device, semi-device independent, and device independent. I start with trusted device. In the trusted device, the user needs to trust on the performance of the devices. As a simplest example, you can think of a laser source and beam splitter followed by two detectors. This laser source sends the polarized light into this polarizing beam splitter. Depending on the polarization of the incident light, the photon reflects or transmits. So depending on this detection event, the random numbers can be generated. But consider the case that this laser source or the source is controlled by an adversary. So she can prepare a entangled pair, keep one and send the other one to the measurement state, which is here. So the user who trusts on the performance of the devices believe that this process is a random process, but of course, Eve knows everything. Okay, despite the fact that this type of generators can be fast, cheap, easy to implement, but the security can be compromised. On the other side, we have device independent, which there is no assumption on the performance of the devices, and it is based on violation of bail inequality. Simplest example could be sharing an entangled pair between two parties, depending on the input-output correlation, and if they can violate the bail inequality, some random numbers can be extracted. This type of generators offer the highest level of security, but at the same time, it is really complicated and also slow. So it is really far from being practical. Here we have an intermediate approach called semi-device independent protocols, which depending on the needs of protocol, some assumption can be made on the devices. For instance, source device independent or measurement device independent, and etc. Here, or this here, I show a source device independent quantum random number generator, which we recently published on arXiv. We can find it with this identifier here. We showed that unbounded amount of random numbers is extractable when the number of POPN goes to infinity. Making a long story short, this type of generators, which is semi-device independent protocols, offer a great trade-off between ease of implementation, security, and also the generation rate. Okay, here we have our semi-device independent quantum random number generator, which is based on prepare and measure scenario. Depending on the input X, state can be transmitted from the preparation part. The single assumption on the preparation part is to bound the energy of the prepared state, while there is no assumption on the measurement part, so it can be seen as a black box. Though the preparation part can be seen as a gray box since there is a single assumption on it. To give you an intuition how this single assumption works, consider two coherent states represented by these two poles. When they're well separated, it's easy to distinguish them. But as soon as they have overlap, they become indistinguishable. Consider measuring a set of quantum states with high overlap and getting clicks here in the intersection area. It is impossible to understand what is the source of this click. This ambiguity in measuring non-orthogonal quantum state is the randomness source of this protocol. For estimating the security of this protocol, we use conditional entropy. Before talking about the conditional entropy, let's explain what is guessing probability. Guessing probability gives the highest probability that an adversary can guess the outcome of the measurement, knowing the internal working principle of the devices. Since it's a semi-device independent protocol, so the guessing probability should be optimized over all possible measurement and preparation strategy, which is quite complicated. Hopefully, we could guess it as a semi-definite programming or STP optimization, as you can see the STP code here, though I won't go into its detail. So we optimize the condition, we optimize the guessing probability through this STP code. Of course, if you have any question on the calculation or STP code, I will be there to answer your question after this talk. After optimizing the guessing probability through this STP code, we can compute the conditional mean entropy, which gives us the amount of genuine random numbers can be generated per measurement. In this slide, I will talk about homodyne and heterodyne detection, which are two well-characterized continuous variable detection schemes. Measuring light's field quadrature is possible with homodyne scheme, which is accomplished by combining local oscillator and a signal on a 50-50 beam splitter followed by two photodiodes. The subtraction of photocurrent from this photodiode is associated with the field quadrature, though heterodyne detection is nothing but two balanced homodyne detection with 90-degree relative phase shift. So homodyne detection gives information about one field quadrature. So measuring a coherent state with homodyne detection, we will have information about one field quadrature, let's say X. So heterodyne detection gives information about both field quadrature at the same time, having a penalty of extra vacuum state. I won't go into its detail, but I will be there to answer your possible question on heterodyne detection. So measuring a coherent state with heterodyne detection, we will have distribution like this. Another important thing to consider is the phase fluctuation. The phase of coherent state is not constant in time, and it might fluctuate. So for continuous detection scheme, for continuous detection measurement, it's really important to track the phase and somehow actively or passively compensate for the phase drift. I will explain about this phase fluctuation and phase stabilization more in the next slide. As mentioned earlier, heterodyne detection provides information about both field quadrature X and B. So if the phase fluctuates in time, it's easy to track the phase and also compensate for the phase drift. while homodyne detection is information about one field quadrature, let's say X quadrature. When there is no phase, or the phase is zero, homodyne detector shows this two Gaussian distribution, which is perfectly well. But consider the case that the state have 90 degrees of phase shift. In this case, the information is lost. So an active phase stabilizer is necessary performing homodyne detection, though heterodyne detection is needless of any phase stabilizer. Recently, we published a work on semi-device independent QRNG. We use homodyne detection, and there we use a piezo for phase compensation. For more detail, please read the paper, which is here. Okay, let's talk about the many outcome approach. We perform continuous measurement, so we would have a continuous stream of outcome. By partitioning the phase space, we can define the outcome. For instance, we can partition the phase space into two parts, and there we have two outcomes. We can partition into three, or of course, we can also have different configurations. So among all these possible configurations, we realize that this strip configuration, which shows here, which is shown here, always gives the highest conditional entropy. So we only focus on the strip configurations. And more number of outcomes is also accessible with increasing these strips, the number of strips. And when this Li goes to infinity, of course, we have infinite number of outcomes. In this slide, you can see the result of heterodyne and homodyne detection for more number of outcomes. So as you can see here, for heterodyne detection, the conditional entropy is shown as a function of mean photon number. And as you can see, the optimal conditional mean entropy is always the same, even going from binary to 4 outcomes. So the optimal conditional entropy is the same, though there is a small improvement for low mean photon numbers. On the other hand, for homodyne detection, the conditional mean entropy shows a significant improvement going from 2 to 4 number of outcomes. So we consider to increase the number of outcomes even more, with, of course, the strip configuration. So here in this slide, you can see the conditional mean entropy as a function of outcome. When the outcome goes from 2 to 20, you can see the conditional mean entropy increases from 0.3 to 0.5, which is a meaningful improvement. It should be noted that the homodyne detection is sensitive to the phase fluctuation. As you can see here in this figure, when the phase fluctuates from 0 to pi 2 or 90 degrees, the conditional mean entropy decreases and finally drops to 0. Also, it should be noted that when the number of outcomes increases, the optimization problem will be more complex, and the STP needs more time to be executed. And also, the losses is really important and also need to be taken into consideration. So we plot the conditional mean entropy as a function of detector efficiency. As you can see, when the detector efficiency is below 0.6, there's no point using this many outcome approach, considering the complexity coming when the number of outcomes increases. So we find a great trade-off when the efficiency of detector is higher than 0.6. Here is the end of this talk. Let's move to the second part.